I'm going to talk about a new approach to reporting and handling failures in distributed systems. Every fault-tolerant distributed system must handle failures. And typically, this failure handling logic is embedded within the code of these systems in an ad hoc manner. But we are also starting to see systems that function out this functionality. For example, systems like Cassandra, RamCloud, Voldemort, and others implement a failure detector class. So the question we want to answer is, what are the right abstractions for reporting failures to applications? And how should these abstractions be implemented? Well, existing systems typically use timeouts. But timeouts hide fine-grained information about failures. In particular, they do not tell what the problem is or where the problem is. They deliver, in essence, a single bit of failure information. Let's look at some other sources of failure information that the applications can use. Consider ICMP destination unreachable messages. Why is the destination unreachable? Is it a problem in the network? Or is it a problem at the destination? Is the problem transient or permanent? Again, notice that the identical message is delivered for all of these different failure cases. Or consider TCP congestion control signals like TCP acknowledgements or explicit congestion notification. Even though these signals are an effective mechanism to detect congestion, they are hidden from the applications, as they are delivered to a layer below the application. So why do these existing mechanisms and abstractions hide fine-grained information about failures? Well, consider these quotations from David Clark's 1988 paper on the design philosophy behind Internet protocols. My interpretation of these quotations and some other relevant parts of this paper is that the network designers explicitly designed the network to not give fine-grained failure information, because they thought that the benefit of such information is not worth the cost of a mechanism. But we think that we should revisit this design choice, because it is mismatched to today's requirements. Today, we are trying to build large-scale reliable distributed systems using a large number of low-quality, inexpensive, and failure-prone components. As a result, failures are common and diverse. But applications lack failure information. So to the applications, this diverse set of failures looks like just some failure. As a result, they must choose a recovery action that works for all of these failures. But this is problematic because this one-size-fits-all recovery is not optimal for some of these failures. And the end result is lower application availability. Let me illustrate. Consider a primary backup replication system. So the primary serves requests from the clients, and the job of the backup is to monitor the primary and to take over if there is a problem with the primary. And to detect problems with the primary, the backup typically uses timeouts. And this system must also prevent the case that both the primary and the backup consider themselves primary at the same time. So it uses a lease service that grants time-based leases to the primary. So how does the backup respond if the primary crashes and the backup times out on the primary? Well, the backup doesn't have much failure information. It must also consider the case that the network is a problem and that the primary is actually alive. So it must wait for the primary's lease to expire before it can take over, to prevent having two primaries at the same time. But observe that if the backup had more information about the failure, it could improve its recovery. Specifically, if the backup knew that the primary had crashed, then it doesn't have to wait for the primary's lease to expire, because it is impossible to have two primaries at the same time. So this causes us to revisit a design question from long ago. What is the right design choice of an interface for reporting failures? And we argue that the network interface should expose information about failures, as then the applications can recover effectively and improve their availability. In the rest of this talk, I'm going to establish this thesis by first describing details of an interface that exposes failure information, and by describing architecture of Pigeon, a system that implements this interface. And then by describing quantitative and qualitative benefits of this interface to real-world applications. So I claim that the network interface should expose information about failures. This raises a question. What failure information should it expose? Well, one option that we found effective is to expose the individual failure type to the application. That is, tell the application what the failure is. Tell it that the remote process has crashed, or the remote host has crashed, or that there is a network partition. Exposing individual failure types probably conveys enough information to the application to recover effectively. But it is burdensome on applications and on application developers. It is burdensome on applications because now they must understand the failure semantics of each of these individual failure types. And it is burdensome on application developers because if the interface is updated to report a new failure type, then the application logic also has to be updated and recompiled to benefit from this new information. So we need something that is simpler, yet similarly effective. And we thought about this for a while and realized that one approach is to group failures that applications handle similarly. So consider these three failures: process crash, host reboot, and host crash, in the context of a client process monitoring a target process. So what is common for these failures is the knowledge that the specific instance of the target process has lost its volatile state and has stopped executing permanently. So now the client does not have to worry about the case that the target is actually alive, and it can take immediate recovery actions. Or consider these three failures: stale routing state, network partition, or misconfigured network. What is common for these failures is the knowledge that the target right now is unreachable, but it may be alive. So the client has to be careful while recovering, and it may have to use external coordination services to prevent instantiating multiple copies of the target. Also observe that some of the failures in this group, like stale routing state, are transient in nature, while others like network partition and misconfigured network are long-lasting in nature. And the client may want to distinguish between these cases, because it may want to wait for the transient failure to fix, while may want to recover for the long-lasting failure. And a general approach to make this distinction is to report the expected duration of the failure. Or consider this third group of failures: CPU overload or network congestion. What is common for these failures is the knowledge that there is a depleted resource in the system right now. And so the client may want to reduce the load on the system by degrading its service, for example. And to do so effectively, it would want to know which resource is depleted. So grouping failures that applications handle similarly gives us the following highlighted interface. And it may not be the perfect abstraction, but it is one that we found useful for a number of applications. And that gives us confidence in this abstraction. The architecture that implements this interface is pretty straightforward and requires some engineering. So I'm going to go through that quickly. But the really interesting part is the power of this interface, and I'll cover that shortly by looking at actual applications. So the architecture that implements this interface, Pigeon, has a couple of notable design points that I would like to talk about. To get the failure information, Pigeon avoids using end-to-end mechanisms because such mechanisms are slow and generally give inaccurate information. Rather, Pigeon uses local failure knowledge. And to do so, it deploys sensors and relays in the network. The idea of using local failure knowledge is taken from Falcon. But Falcon deploys sensors only at hosts to detect host failures, whereas Pigeon uses it to detect both host failures and network failures. So a sensor is a component-specific module. It is embedded within the component, and its job is to detect failures, local failures. For example, there is a process sensor running on the target host, and it detects process crashes by monitoring the process table. There are link sensors running on the network elements, and their job is to detect link failures by running a keep alive protocol with the adjacent network elements. Then there are relays. The job of the relays is to propagate this failure information to the client end hosts. The interpreter receives this failure information and converts it into a failure report. For example, it receives the status of individual links, forms the topology of the network, checks if there is a network partition, and if there is one, reports an unreachability to the client process. Pigeon must face some other technical challenges. First, Pigeon must detect all possible failures. And it is hard to design and write sensors and relays that would be able to detect all kinds of failures. So Pigeon uses a backstop timeout as a catch-all failure mechanism. And Pigeon must also tolerate failures within its own components. So it must work even if some of the sensors or relays fail. And again, Pigeon resorts to using end-to-end timeouts if this happens. Then second, Pigeon must report expected duration of an unreachability. And that is a hard problem because it is hard to know how long it is going to take for a failure to heal. The current Pigeon prototype uses values based on previously collected failure data. So now that I've talked about an interface that exposes failure information and its implementation, Pigeon, I would like to talk about the quantitative and qualitative benefits of this interface to real-world applications. So recall that as part of the thesis of this work, I said that the network interface should expose failure information, as that helps applications recover effectively and improve availability. Well, it's time to test whether the interface that I presented helps applications recover effectively and improves their availability. And if yes, then how much do all these benefits cost? But first, let me briefly talk about our testbed. Our test network had 16 physical routers running OSPF, a link state routing protocol, and these were connected in a 4-port fat tree topology. And then we had 12 hosts in the form of virtual machines connected to this network. So what is the effect on availability of distinguishing between host and network failures? I'm going to answer this question by revisiting the primary backup system that I talked about. So recall that the primary serves requests from the clients, and the job of the backup is to monitor the primary and to take over if there is a problem. And recall that there is the lease service that grants time-based leases to the primary to prevent both the primary and the backup considering themselves primary at the same time. We configured the lease service to give 10-second leases, which is pretty realistic. Even Google's Spanner uses 10-second leases. Then we injected a segmentation fault at the primary at a time chosen randomly into the experiment and measured the system downtime as seen by the client. And we observed that with unmodified primary backup, the client saw a downtime of 6.9 seconds on average, because the backup could not distinguish between host and network failures using timeouts, and it had to do the long recovery of waiting for the lease. Out of these 6.9 seconds, 5 seconds is the expected time the backup takes to wait for the lease, and the rest is the time it takes for the client to switch using the backup. But with Pigeon, the client saw a downtime of only 1.6 seconds, because Pigeon said that the primary has actually stopped, and so the backup could recover quickly. So I said that Pigeon gets more information about network failures. So what is the effect on availability of reporting these network failures? I'm going to answer this by looking at Cassandra, a distributed storage system. So Cassandra keeps copies of data on multiple replicas. And during normal operation for read requests, it selects a primary replica from which it fetches the data, and then selects backup replicas from which it fetches the data of the digest for the data. And then it matches the data against the digest and serves the request to the client. There is one notable aspect of Cassandra that is relevant to our discussion here. So the coordinator uses the smallest average latency of past requests to select the primary replica from which it is going to fetch the data. So we ran unmodified Cassandra, and Cassandra integrated with Pigeon and integrated a transient routing problem in the cluster and measured the client's throughput. And we saw that for unmodified Cassandra, the client almost blocked after the failure. So the y-axis here is throughput of the client, and the x-axis is the time into the experiment. And the reason that the client blocked is that the coordinator kept on selecting the same problematic replica as the primary until the point the average latency of this replica became bad enough for the coordinator to stop selecting it. So the end-to-end mechanism of using latencies does not really react quickly enough to failures. But with Pigeon, Cassandra, the coordinator in the Cassandra could quickly switch to a new replica, and that helped improve systems availability and the client's throughput. So does the interface that I presented help applications recover effectively and help applications improve their recovery decisions? Well, I'm going to answer this question by looking at RAM Cloud. So RAM Cloud has master servers that store data in memory, and then it has backup servers that store data on disk. And during normal operation, the master server serves requests from the clients, and it replicates data on the backups for durability. And if there is a problem with the master, recovery masters take over. They quickly reconstruct the data that was on the dead master from the backups. So there is one aspect of RAM Cloud that is relevant to our discussion here. RAM Cloud uses a very short timeout to detect problems with the master of a few hundred milliseconds typically. And this short timeout may fire even during transient problems and may cause RAM Cloud to recover. So to test this, we ran both unmodified RAM Cloud and RAM Cloud integrated with Pigeon injected a transient routing problem in the cluster and observed the number of times RAM cloud recovered. And we saw that with the short timeout, unmodified RAM cloud recovered each time, even for this transient problem, when the recovery was unnecessary. But Pigeon helped RAM cloud avoid this recovery. And it is important to avoid this recovery because, first, it is unnecessary as the client sees the same downtime, whether you recover or not. And second, recovery in RAM cloud is very expensive because a lot of data is transferred from the backups to a bunch of recovery masters in a very short amount of time, and that puts load on the network. So Pigeon helps RAM cloud avoid this unnecessary and expensive recovery. There is more evidence to suggest that the interface that I presented helps application recover effectively. So recovery is an application-specific decision. Well, and the interface that I presented helps application recover in their own ways. So for the same transient routing problem, the interface let RAM cloud wait for the problem to resolve. Well, and it helped Cassandra, the coordinator in Cassandra, to optimize its replica selection and pick a non-problematic replica. So how much do all of these benefits cost? Well, running additional logic in the system and then transferring failure data has CPU overhead and network overhead. And we measured this overhead. We found the CPU overhead at each end host to be about 3% and at each router to be about 0.3%. And we found the network overhead to be about 2 kilobits per second, which is about 5 orders of magnitude less than the bandwidth of a gigabit link. And in terms of implementation burden, the current Pigeon prototype has about 5,000 lines of code, and it was fairly straightforward to integrate Pigeon with RAM Cloud, which took about 70 lines of code, and with Cassandra, which took about 400 lines of code. So I'm going to go through some related work quickly, other than the work of failure detection that I've already talked about. So there has been a lot of work in the area of network monitoring. And this can be divided into based on 2 axes. So what failure information is gathered, or what information is gathered, and who is the intended recipient of this information. And there is a lot of work that exposes the state of the network for operators to perform diagnosis, for example, and for end hosts to perform traffic engineering, for example. And all this work is complementary to Pigeon, and Pigeon can borrow from these mechanisms. And in fact, it does. And then there is also some work that exposes failure information to applications, but the goal of that work is not to present a comprehensive failure abstraction to the applications. So to summarize, I asked the question, what are the right abstractions for reporting failures to applications? And then I argued that the network interface should expose information about failures, as that helps application recover effectively and improve availability. Then I showed you a simple yet effective abstraction that exposes, differentiates between host and network failures, transient and long-lasting failures, and also gives warnings. And I also demonstrated that this interface is not too hard to implement, and it provides sizable benefits to a variety of applications at low costs. Thank you.
So Pigeon focuses on stop failures. I'm curious what it might take if you wanted to also handle Byzantine failures.
Oh, so the question is, can we handle Byzantine failures, or what it will take to handle Byzantine failures? Well, this system is only for crash failures. We haven't thought about how to handle Byzantine failures. And I'm not sure if there is a Byzantine failure detector as such. I mean, it would be good to handle Byzantine failures, but we haven't done it yet.
Hi, Naveen Dajan, Microsoft Research. Really like this work. My question, I guess, is more on the clarification side. How do you ensure that the notifications that you're sending to the application reflect the ground truth? For example,
I cannot hear you.
Reflected the ground truth. So for example, whatever you tell the application could be inconsistent with what the true state looks like. For example, you said the replica is unavailable or has crashed, while just after you send that notification, you actually receive back from that replica a message. So who does the conflict resolution now that you're seeing 2 conflicting updates about the state of the system? Okay, so first, if a stop condition is reported to the application, then it ensures that, Pigeon ensures that before it
say stop, that the server or whatever it is has actually stopped. It ensures that, it confirms that the process has crashed by looking at the process table, for example. In case of network failures, so in our current prototype, it fetches the topology from the, a server fetches the topology from its gateway router. And that is consistent. And that represents whatever is the state of the network right now.
But isn't it an asynchronous distributed system?
Yes, it is asynchronous distributed system, but I think the only thing that matters to the client is what is the state of its router that it is connected to. Because that is what governs routing, right? That is the logical state of the network.
Okay, thank you.
Hi, Mike Freeman. I guess a follow-up on this. It seemed like one of the problems you encounter is the same thing that end-to-end testing is introduced for, is that in many cases you can't actually tell the difference between a particular node crashing the system and the network being unavailable to it. So if you were using this in a larger distributed system, and in different parts of the network, a particular node would be available, in other parts it wouldn't, because of some, in this case, it would actually be due to a partition rather than a node failure. Do you have a sense of how this would actually help you use that information to build a better system? Because kind of to follow up his question, you're actually getting conflicting reports. One node says there's a network or host failure, the other one doesn't. It seems like in the application space, you're still needing to then kind of use end-to-end.
So is your question that if there is a network partition, then one side of the partition may say that the host has failed, while the other side of the partition may say that the host hasn't failed?
Or even just link failures, not even actually true network partitions. You're going to see conflicting information in different parts of the network, because you might actually see a link failure before the network reconverges.
Right, so that may happen. For example, some client may see that there is a network failure right now, and Pigeon will say that there is a failure, but other side of at some other node, it will say that, oh, that failure hasn't happened yet. So why is that problematic? I mean, that client will say that, okay, there was this failure, it will report that failure to the application, and the other side, because it does not affect it, so it wouldn't report it as the failure.
So in that case, you'd still need the same application recovery, it would just speed up detection time.
Pardon?
You'd still need the same application recovery, it would just speed up detection time.
I still do not understand your question.
Okay. Anyway, I was saying you would still need the same application recovery and application mechanism. It would just speed up detection time.
Yeah, I mean, the application recovery wouldn't change, right? The logic of the application would not change. So,
okay.
All right.
Thank you.